In Concept B, we're going to be focusing on how to write nuclear decay equations and also how to predict a couple of different things with them. So the goal of this topic is to determine the type of decay and then write the nuclear decay equations. We're going to be completing nuclear equations and predicting missing particles, whether they're reactants or products, and also learning how to distinguish between natural and artificial transmutations. So just a little to start with that. Natural is going to happen with any unstable atom. So this happens spontaneously on its own. So this can include alpha, beta, and positron emissions, which we've talked about. There are also a type of transmutation that's called artificial. This occurs with stable atoms, and they need to be hit with some type of high energy particle that then makes the nucleus unstable and then forces an artificial decay to occur. So this can be what we're going to focus on today, which is bombarding of any nucleus, but we're also later going to be talking about fusion and fission and how that's related as well. So one little thing to review, remember our atomic notation here, where we have our element symbol, and then the mass number is the higher of the two numbers, the superscript, and atomic number is the lower of the two numbers. Also remember that the subscript provides us the nuclear charge, or in general the charge of the particle. So just keep that in mind. I'm going to be referring to it mostly as charge instead of atomic number, just because it will tie in more with our beta particles and positrons and so on. Also remember that our atomic number always determines the element. So if I can figure out the subscript number, I can then look up my symbol. So just keep that in mind. That's probably one of the things that students miss the most about these decay equations. So when we write these decay equations, they differ from balancing chemical equations because instead of balancing the atoms present, the mass numbers and atomic numbers or charges are balanced. So this is going to be very different from when later in the year we talk about balancing equations. Here we're actually balancing the mass numbers and charges. Now the sum of the mass numbers or charges on the left has to equal the sum of the atomic number or charges on the right. In addition, the sum of the mass numbers on the left must be equal to the sum of the mass numbers on the right. So our reactants that are on our left have a total mass number 14. If you look at the blue mass numbers on the right, together they add up to 14. So again, left and right have to equal each other. Same thing with the charges on the bottom. On the left I have a total of 6, and then on the right I need to make sure I also have a total of 6. So 7 plus a negative 1 equals 6. So both mass numbers and charges are balanced in that equation. So mass and charge must always be conserved. And then here's another example, and I would like you to kind of label a couple of things on your note packet. So again, the blue numbers are my mass numbers, the bottom numbers are my atomic number, which is also my charge. So if I check the left and right here, 283 is equal to 234 plus 4, so that checks out. I basically placed an arrow or an equal sign where the arrow is, and then again I'm just adding anything together on each side and checking that they match. And then same thing on the bottom, 92 is equal to 90 plus 2. So again, both mass number and charge are balanced. Oops. And you can see there again. So if this was my missing particle, okay, I would get my 234, I would get my 90, and then how I got the TH is from using the 90. And that would be my completed answer. So natural decay equations, this is a result of an unstable neutron to proton ratio. Remember we talked about this in Concept A. These natural decays occur because that nucleus is unstable. It's because of that proton and neutron ratio. Since this is a natural decay, the unstable isotope is the reactant to the left of the arrow, and there's nothing else there that is the only reactant to the left of the arrow. I think in your note packet you have a blank here, so just put is the only reactant to the left of the arrow. In order to determine the type of decay that an isotope will undergo, you have to look at table N. So on table N, I can look up my decay mode, and I can see that, say, carbon-14 is going to undergo beta decay, while calcium-37 is going to undergo positron. So having table N when we get to doing some practice problems is going to be important. So let's look at an example of alpha decay. We discussed a little bit in Concept A that the nucleus is going to lose 2 protons and a total of 4 particles, so 2 neutrons as well, and it turns into a different element. So here I'm going to look at plutonium-239. I'm going to write out the information that was given to me, and I'm going to use the periodic table to look up the atomic number, which is also my charge, which is in red. Okay. Remember, the plutonium-239 is the only reactant that's on the left. I can also double check that it's an alpha decay by looking it up on table N, seeing that the alpha sign in the decay mode Okay, and then if I look up the alpha particle, I can see that it's the nucleus of a helium atom. So the 4, 2, and then He. So I'm going to fill that in first, and then I'm going to basically determine through calculating what my new nucleus is that plutonium transmuted into. So I'm going to see that my mass number has to be 235 in order for 235 plus 4 to equal 239. And then my charge or atomic number, if you can see the math right here, 94 is equal to x plus 2. 94 minus the 2 gives me a 92. And then make sure with these nuclear decay equations, we're transmuting and changing one element into another. So plutonium cannot stay plutonium over here. We have a new atomic number. So if I look up 92 on the periodic table, I find that it changed into uranium. All right, beta decay is when a neutron in the nucleus decays to form a proton and an electron, which leaves the nucleus at a high speed. So really when we talk about beta decay, we're talking about an electron leaving the nucleus, but it's actually, if you can see here, originally coming from a neutron. And we'll go back to that in class tomorrow, because that might be and should be a little bit strange to you. All right, a beta decay example is cobalt-60. Okay, I write down the information given to me, I look up the atomic number of 27, I then look at my table which confirms that it's beta decay. Okay, I look up my symbol for a beta particle and I fill that into the equation on the right because it's going to release this beta particle. I'm then going to look for my mass number and then very carefully make sure that you get that 27, if it's equal to x plus a negative 1, means that my x has to be 28. This is a very common mistake when doing beta decay. And then finally, I have to use the 28 to get the symbol. So I look it up on my periodic table and find that it's nickel. And again, a lot of students make the mistake of putting this down as cobalt, but in nuclear chemistry, we're transmuting and changing that element. And because of the new atomic number, that tells me that I have nickel as my new element. And then finally, positron decay. This is where we're going to basically be having an antimatter particle of an electron, which is called a positron, that leaves the nucleus at high speeds. All right, so now we're going to give an example of iron-53. Iron with its mass number 53 in blue, and looking up the atomic number, I can confirm that it's positron decay on table N, and then I can look up the symbol for a positron on table O, write that down, and then I'm going to balance the masses and charges. So I get 53 and 25, and then I have to use the 25 and the periodic table to look up the new symbol, so manganese. Okay, now artificial transmutation, this is a little bit different. Before in natural decay, if I go back to that, I only have one particle on the left. So this is happening on its own, it's spontaneously. However, artificial transmutation, I have to take the atom or the nucleus of an element, and I have to bombard it with high energy particles to force what would be a stable nucleus to an unstable one. So my mass numbers and atomic numbers still have to be balanced on each side of the equation. Okay, so 15 plus 1 is equal to 12 plus 4, so they're both equal to 16. And on the bottom, both of them are equal to 8. So just because I have an extra particle here, mass and charge should still be conserved. All right, so two examples I'm just going to show you. Here again, I can recognize that it's artificial and not natural because of the two particles on the left. I'm going to strike the nitrogen with the neutron. So I'm going to go out finding that over my left, I have a sum of 15, which means that on my right-hand side, 14 plus my missing 1 will balance out the mass. And then on the bottom, to balance out the charge, I need a 1 as well. If you look on table O and you look at the notation 1 over 1, and also if you look on your periodic table for the atomic number of 1, you'll find that you have hydrogen as an additional particle of this artificial transmutation equation. And then finally, identify the radioactive isotope that originally decayed, that formed phosphorus. Same idea, I'm going to balance out my mass numbers. 31 is on my right, so 31 minus 4 gives me 27. I have 15 on my right for my charge. 15 minus 2 gives me 13. And then I use the 13 to look up the element symbol, which is aluminum. And again, this is an artificial transmutation because I have two particles on the left. So the alpha particle is going to be bombarding into the aluminum, which forces it to transmute. Okay, that's it. We're going to do a lot of practice with these over the next 2 days. So just come in with your questions and we'll move from there.